All right, so this lecture is on expanded octets, and now we're going to talk about VSEPR, which stands for valence shell electron pair repulsion. So we've mentioned expanded octets before, but we're going to, I guess, have a separate presentation on it because a lot of it's not complicated, but a lot of kids tend to confuse what happens if you have more than 8 electrons. So just to review here, our steps for Lewis dot structures. The first thing we want to do is count our valence electrons. So again, we get this from the periodic table, figure out how many valence each element has, and then we add them up. And if we have an ion, remember we have to account for the charge of the ion when we're getting the total number of electrons. So if an ion is negative, that means that we are adding electrons because it's negative. So that means it must have more negative things. And if the ion is positive, then we're going to actually take away electrons. Steps 2 and steps 3, remember we draw our skeletal structure for the compound. So like the basic form connecting with single bonds. And we're going to connect atoms to each other again with those single bonds. The hydrogen atoms are always going to be on the outside with one bond. Remember, hydrogen atoms are happy with a duet, and we have a few other exceptions. Remember, H, He, B, Be. So hydrogen and helium are happy with a duet, and then boron and beryllium, remember, do not need an octet. As a reminder here, okay, the more electronegative elements go in the outside positions, the less electronegative elements, except for hydrogen, end up in the center. All right, after we've drawn our skeletal structure and connected with single bonds, we are going to distribute the extra electrons left over. So we're going to finish our octets on those terminal or outside atoms first, and then we put them on the central atom if there's any extras. If the electron number is not exactly right, so now we're talking about not having an octet. If we have too few, so let's say we have that central atom that only has 6 electrons on it, maybe like 3 bonds or something. So that would be too few. So that we would form double or triple bonds, if necessary, by moving lone pairs from terminal atoms and making them bonding electrons, aka bonds, with the central atom. If we have too many valence electrons, or too many valence electrons on an atom, we can expand the octet. All right, so basically, if you have more electrons left over, what we're going to do is tack on more lone pairs onto that central atom. This only works if we have an element in the 3rd period or 4th period, 5th period, 6th period, 7th period. The reason why is, remember, in that 3rd period, 3D, that's where we add on those 3D orbitals. That's 5 orbitals that can hold 10 more extra electrons. So those elements can actually have more than an octet because they have somewhere to put them. They have those extra orbitals. But again, only in period 3 or higher. All right, so elements in period 1 and 2 cannot expand their octets. The other elements can if there are too many electrons after all of the octets have been completed. Okay, so let's go ahead and do some practice. So we've got PCl5. So I'm going to count up my total valence. So phosphorus is in group 15, so that's 5 valence electrons, plus I have chlorine, which has 7 valence electrons, but I've got 5 total chlorines. All right, so that looks like it's going to be 35 plus 5. I have a total of 40 valence electrons. All right, well, let's draw our skeletal structure. We'll have phosphorus in the center, and then we have 5 chlorines. So I'm just going to start drawing them around this phosphorus. 1, 2, 3, 4, 5. All right, connect with single bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so remember, I'm counting 2 for every bond because 2 electrons are shared in a bond. All right? So I've just added 10 electrons. So that means that 40 minus 10, I've got 30 more to go, right? So I can start drawing those. So so I've got 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay, so if you take a look here, all of our chlorines have fulfilled octets. So I'm just going to count the top chlorine's octet because all of the other chlorines look like it. All of them have 3 lone pairs on them with 1 bond. So that's 1, 2 from the bond, 3, 4, 5, 6, 7, 8. So all of the chlorines are happy. So I'm going to go back and count the octet and the phosphorus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this one actually has more than an octet, so more than 8 electrons. So we can just check where it is on the periodic table. Phosphorus is in that 3rd period, so this Lewis structure is totally valid. It's fine for it to have more than an octet of electrons on it. Okay, so this is our final answer here. All right, and if we were practicing naming, let's just kind of do a quick recap here. We know that this is a covalent compound. We've got phosphorus, no mono on that first element, and then chlorine changes to chloride. All right, and we'll add our prefix. So 5, the prefix is penta. All right, so phosphorus pentachloride. Okay, if we look at the next example, we have xenon difluoride. All right, so xenon is Xe, and then difluoride, so that means I have 2 of them. All right, well, let's get our total number of valence electrons. Xenon is a noble gas. So noble gases, I know we've talked about how like they don't form bonds. Sometimes they do, it's very rare, and most of the time it's like xenon or krypton that form these bonds. But that's okay. We can still draw the molecule because we have a nonmetal and a nonmetal, so we know we can draw our covalent structure here. So xenon has 8 valence electrons, plus fluorine has 7, but there's 2 fluorines. All right, so it looks like I've got 14 plus 8. All right, 22 electrons. All right, well, let's draw our structure. We have xenon. I'll make that the central. And then we have 2 fluorines. So I'm going to make it symmetrical. Draw 1 fluorine here, 1 fluorine here. And here's my single bonds. So 1, 2, 3, 4. All right, I need to get all the way up to 22 so I can start putting lone pairs on those terminal atoms. So far I've drawn 4 electrons with the bonds. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. All right, so notice how I ran out of space on the fluoride atoms, and so then I started putting lone pairs on the central atom. The reason I did that is because fluorine is not in the 3rd period. Those elements cannot take more electrons. So anytime that you have an expanded octet or you have enough like electrons where they don't fit on those terminal atoms, just start tacking them onto that central atom. All right, so let's just double check our octets. Fluorines look like they're happy. 1, 2, 3, 4, 5, 6, 7, 8. Same thing here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so fluorines are okay. Now if we check xenon, we can tell kind of by looking at it, there's more than 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, but xenon is past the 3rd period, so it's okay for it to have more than an octet. All right, so this is our final structure for xenon difluoride. All right, so now VSEPR. This is just a way of visualizing what these molecules would look like in real life. Okay, so far we have only drawn two-dimensional shapes with our molecules. We know, though, that our molecules in real life are not stuck on paper, but rather they have three-dimensional structures whose shape informs its function. So that just means like it's going to affect how it bonds, it's going to affect its polarity and a few different things. So VSEPR actually stands for valence shell electron pair repulsion. All right, so that sounds like a really fancy way of basically saying electrons repel each other. All right, so when we draw our structures, again, two-dimensional shapes, in 3D, let's take a look at for example, the molecule on the left-hand side. It's not going to be this like star shape over here, and be like totally flat. What's actually going to happen is that each of these chloride ion or chlorine atoms on the ends here, these guys are going to separate as much as possible from the other chlorine atoms because of all these lone pairs. So like we talked about before, electrons have a negative charge. If an electron comes in contact with another electron, negative and negative, those guys are going to repel. So they want to be as far away from each other as possible. And the same is true for electrons that are in a molecule. They don't want to be next to each other. So like, for example, these two chloride atoms are going to like be stuck right next to each other. They're going to try to spread out as much as possible. All right, so we have VSEPR to help us predict what kind of shapes the molecules will form. So the first step is we need to be able to draw a Lewis dot structure, which is what we've been practicing for the past 2 days. If you can't draw that, then you can't predict the shape. So we have to be able to do that first. All right, so again, we're going to focus on the repulsion of electron groups on interior atoms to maximize separation. Electrons are negatively charged, like charges repel each other. So around the central atom, areas where electrons are located, we're going to call those electron groups, are going to try to be as far away from each other as far as possible from other electron groups. So electron groups can be lone pairs. Okay, so like this is a lone pair. Single bonds, multiple bonds, so double or even triple bonds, or even a single electron. We're not going to worry about these, but it's possible. Or anything that has electrons. They're going to try to stay as far apart as possible. So the first thing we're going to look at when we're trying to decide a molecule's shape by using VSEPR is we're going to look at the geometries around the central atom. All right, so basically, there's 5 shapes that we're going to look at. Okay, and these are known as electron geometries. Okay, so we're going to have electron geometries and then something different, but these guys are electron geometries. All right, so electron geometries is the shape that results from the groups of electrons repelling each other. So this is like the general shape, and then molecular geometry is going to tell us more specifically how many lone pairs versus bonds we have. All right, so rating Lewis dot structures. From Monday's class, let's just take a look at this example that we drew. So we drew phosphorus trichloride. So in the Lewis dot structure, there are 4 electron groups around the central atom. That makes this electron geometry tetrahedral. So for electron geometry, I'm going to use the red highlighter. I'm going to look at this structure here, okay, this guy, and we're going to identify how many groups are around the central atom. By groups, that can mean bonds or lone pairs. So here's 1, 2, 3, 4. That's how we got there are 4 electron groups around the central atom. Right? That makes its electron geometry tetrahedral. I'd get that from a chart that looks like this. So we said that there were 4 areas of electron density. So this is what we're talking about. All right, so that means that the electron pair geometry is a tetrahedral. Okay, so in general, like a 3D shape, this is what it would look like. Now, if I go back up here, I would identify, hey, 3 of these are bonds, and I do have one lone pair on that central atom, this guy right here. So because of that, I can specify what my molecular geometry is. So here's molecular geometry. And again, if you look at what it's, the way that it's classified, it identifies, are there 0 lone pairs on that central atom? Is there 1 lone pair and the rest are bonds? Are there 2 lone pairs, 3 and 4, and so on? So we know that we have 4 areas of electron density. So in general, we have a tetrahedral shape. But if I go back up to that molecule, one of those is a lone pair. So I can say 1 lone pair. The molecular geometry of that molecule is trigonal pyramidal. All right, so those 3 chlorine atoms, is chlorine, right? Yeah. The 3 chlorine atoms would be like represented by these green dots here, now blue dots. And then the lone pair would kind of stick up into space. So trigonal pyramidal. So they make like these guys at the bottom, make like a 3D little pyramid with 3 sides on it. All right, so again, that's where this comes in. One of those groups is a lone pair, so the molecular geometry is trigonal pyramidal. All right, so on a test or a quiz, you will be, you'll have to remember, I guess, these different shapes, but we'll get some more practice in before then. All right, hopefully that helped. And we will do a lot more practice with determining electron and molecular geometry, so you become more familiar with that.